Right. Let's get started. Can you hear me? Okay. So first of all, the slides are available online, so you can log in our e-learning system. There is a third announcement, and there is a link there, and you can download the slides. So I hope that can help you to follow the lecture today. So today we are going to talk about some topics. The 2.3, the digital camera, 3.2 color, 3.2 linear filtering, and the favorable filtering and the example of linear filtering. And also the 3.3 section, the linear filtering and the bilateral filtering. But this is your textbook, you know it, right? The free online textbook, you can download it and read the chapters by yourself. But of course, I will try to cover the sections I think is useful to you. Okay, first, I want to, because all of you need to do your homework 1, 2, 3, 4, and you need to present that. But I'm not sure whether all of you are familiar with the OpenCV. That's the requirement for our first homework. So I want to make a brief introduction to the library. First, there are free resources you can obtain. This is the book, okay? It is available in our school library, and I borrowed it, and I think it's good for you to take a look. So could you pass the book around your classmates? And the second book, the right one, it is a e-book, okay, either in PDF or in EPUB format. It is available at our library. Once you log in our library system, you can download the file from, because you are a student, you have the account. Okay. And the book I downloaded is very short. Okay. So let's take a look. Okay, it's like this one, and you can find a lot of examples in the book, and of course, it's up to you. What is the research interest you are looking for? Then the book available free from our library, because our library has purchased it already, and you all have the right to access the book. Okay, so it's short and contains a lot of code. And all of them are OpenCV related code. If you want to get more like resources, there are, okay, this is a free online book. But it is slightly older. It was published in 2012, but the code is still available. And it's free. You can download it for yourself. And for this book, it is not a free book, but the publisher offers a 7-day free trial. If you would like, you still can and use the trial version. It's totally the same as the book. You need to pay for it. And another advantage of this book is all its code is shared on GitHub. So if I should say, if you want to save your time, use their code. It's okay. And also there are a lot of online tutorials. Let's see this book, for example. Okay. The video. Okay. And another one. Okay. First of them are available at YouTube, and it's free and very long. The first one lasts for 9.5 hours, and another one lasts for 3 and 7 hours. So if you like, you can spend your time and learn their knowledge from YouTube. Okay, I want to show you an example what you can do for your homework 1 and 2. Given an image, so it is not taken by me. This is just an image found from Google and downloaded. So you can see the background. That is the National Pest Museum in Taipei. Okay. And there are several people. They took a picture for their memory, but however, there is an unrelated pedestrian at the background. Okay. It is a common case we will encounter. But so you can assume you now have a test. You want to remove the background pedestrian using OpenCV to do it. The task has a name. It means implanting, and there are some tutorials online to teach users how to use OpenCV to do it. Take a look. Great. All right. I don't want to spend too much time on it. But this is another example. If the authors want to remove this mark from the person, what did he do? Okay, so how to create a map, and then you follow the 10 steps, you can generate a similar result. So the message I want to deliver to you, there are a lot of free available resources online, and you can utilize them for your homework. Okay, so what I did is first I created a mask image. So the region here, the region here is the district and the background. So you can see there is a similar shape. Then how to create a mask image? I use a free photo editing program. It's called GIMP. The full name is GNU Image Manipulation Program. And it's free, it's powerful, and it supports Windows, Linux, and Mac OS. Then, okay, this is my code. It's very simple. And first line, import CV2. So like can use OpenCV. So what's the difference between CV1 and CV2? OpenCV is a library, and in the beginning, it was implemented in C language. So the library will become imported CD, and then it was implemented in C++. So the library name changed to CV2. Then my fourth slide is CV2 that I read. So I read the photo, and then I read the mask on line 6. Then I use the intent function here. Okay, this is my input image, my mask, and the parameter here is how large the algorithm. So this is the algorithm we need to specify. There are two algorithms supported by OpenCV. One is TEDIA, and another is NS. Okay, that on line 8, I will get my result, and then I dump it out, then I get the image. So what's the difference between the number 3 is the radius required by the two algorithms. And what are the two algorithms? First of them are papers published in different journals. Okay, the first one was published in 2001 at CPR. I mean, it is the top conferences for the region. And another one is published in 2004 on a journal. Okay. And both algorithms require no training image. It just use pixels surrounding the mask area to fill the data. And let's see the performance. Okay. For the NS algorithm, when I set different radius 3 to 33, so you can see when the radius is 3, I see a quite large contrast between the upper and the center area. When I set a larger radius, say 33, then it becomes blurred. But the result is not good. And let's see another algorithm here. Okay, for a small radius 3, it looks similar to the NS algorithm. But when the radius is large, okay, the background is almost blurred out, very smooth. And this is the result. If I set the algorithm as TDR and the radius is 33, okay. And the first glance, I didn't found that, okay, there is a pedestrian at the background. But however, it looks slightly, if I pay attention there, I will find something wrong. So the question is there any better algorithm? Okay, and yes, there is. There is a implanting algorithm published in 2018 in new apps. Okay, sorry. The conference originally was named NIPS, NIPS, but NIPS is okay. The sound is the same as an organ in our body, so it's not so elegant. So it changes name to neural IPS. And okay, the algorithm requires a lot of training image to train the neural network to restore the missing regions. And they generate okay, this is their result. For the white blocks, all of the images are missing. And this is the images restored by their algorithm. It looks quite nice. And even for face, it works. If we crop out a very large region from the given image, this is a reconstructed result. This looks like quite realistic. even you you hardly find some artifacts on the reconstructed image. And for buildings, okay, it looks like. So because it requires many training images, so the reconstructed result will depend on the training image. Okay. Okay, and okay, I will do a last demo for you. Okay, OpenVINO is another library, so you will use OpenCV for your homework one, right? And then OpenVINO is another library provided by Intel. So the OpenVINO use a lot of neural networks. So you know now many people use NVIDIA's GPU to train or to run their neural networks, right? And then Intel has an idea because Intel is a CPU manufacturer. They have a lot of knowledge about the CPU and they know how to accelerate it because they have their special instructions built for their CPU. So they developed the OpenVINO library. We can run neural networks on CPUs rather than on GPU. So let me show you if I successfully install, then I run it. There is an image like this. And then you can see this is the brush size, this is the radius. And I can select a region and then run it. And wait a few seconds. Okay, this is the generated result. If I think it's not good enough, then I can reset and change my radius and create another and run again. All right, is this look better? I'm not sure. And yes, I want to show, okay, see the difference. I can use tab. Okay. So all of you can install the OpenVINO library for yourself because it's free, available online. And then let's make a comparison. So the leftmost is the input image, middle is the algorithm published in 2018, and then this the rightmost is the TDS method. So what we can see is one's method reserves the structure. So you can see the page here continued until the process on, but the TDS method cannot do it. So that is the improvement for impending algorithm. And there are more questions. Are there better algorithms? Because once the method was published in 2018, and now it's 2023, there are 5 years gap. So is there any better algorithm? So this is the beginning of a research project that you can do. Okay, so there are some questions. Is there any new impending algorithm published in recent top conferences or journal? Okay, if I use IEEE Explore ACM digital library, can I find any useful papers for this test? So first of all, have you used the IEEE Explorer? Did any of you use the search engine for? Okay, one and others. Okay, and did you use ACN digital library before? Okay, so maybe I need to show you a live demo. Okay. Okay, this is the search engine, and IEEE is an organization, International Electrical Engineering, etc. Developing something intending. Okay, and go. There will be a lot of results, just the long list. So, and if you want to show the latest one, and this is published this year. Deep learning based projection domain network. It looks like not for the everyday problem. Imaging based image correlation, multi-resolution feature projection. Multi-scale research solver for total rate. This is intending. What I want to show is IEEE is program and the ACN digital library are both search engines for academia papers. So you can find research topics or useful papers for your own projects or tasks or projects. Use the two search engines to help you search. And, okay, and when you read those papers, you can ask yourself a question. So what are the assumptions? For example, because you see the example of TDR and NS, their assumption is the missing area is a long safe line, so that they can find the similar pixels and the boundary and copy their values to the missing area. However, for our museum photo, the assumption doesn't hold because our area is too large. There are too many missing pixels. So if their assumptions doesn't work, so what can you do to develop a better algorithm to match your new assumption? So that's the one's algorithm because it exploits a lot of training data to find the relationship between the missing region and any other regions in the image. However, if you do it this way for your homework, this will be great because all you can. So I said, most of you are graduate students, right? And you are going to do your own research and write your thesis or dissertations. So if you do it for your homework, that'd be great. Also great for your thesis and dissertations. But it takes time and effort because you see there are a lot of paper to read and to think about and even implement those algorithms. But however, it's good for you. Okay, let's go back to the last slide of our previous week. So this is the structure of our eyes. And what I mentioned last week, the structure of an eye is very similar to a camera because we have lens, it can adjust the focal length like a camera. And we have iris, it can control the input light amount, vertex light, the shutter and aperture. And finally, we have the retina. It's like the film can sense the light. And we are going to see more details about the retina. So for retina, there are several layers. I was not I was not an expert for medicine science, medical science. I only have the concept. So if you have the, I should say, advanced knowledge for medicine science, don't be shy to share it with us. So what I want to say is, there are several new cells on the retina. Okay, so for us, the most important one are the rod cell and the cone cell. They are rod and cone because their look. Okay, this is their look. We enlarge the region. So this is I should use. Okay, so this is a cone cell. It looks like cone. It has a long outer segment, and this is the cone cell. So this and this also cone cell. It is short and like a cone. So they get a name from their shape. And this is a brief introduction how neurons or neutrons communicate with each other. Right? So this is a cell, and this is another neutron cell, and they can should say one cell send the messages to another cell through a synapse to another one. Okay, so for one cell, it receives many signals from other neutron cells, and then it do something. It sum those input messages up, and sometimes it amplifies the electrical impulse, and sometimes it reduce the electrical impulse, and then send it out to another neutron cell. So this is a biological action. And in computers, we developed artificial neural networks in the same way. For an unit, there are several input values, and then we sum them up. Through an activity function, we send the signal to another layer. But if we have several layers, we will call it deep neural network. Okay, let's look at another look. So why those rod and cone cells can sense light? Okay, because this is the structure for a rod cell. This is the nucleus, and this is outer segment. It's very, very small. How small is it? As small as 1 neurometer. And this is the structure. Within the outer segment, there are many photopigments. When the light within a speak wavelengths, it will interact with those segments. Then there will be electrical signal delivered out from the road and cone cell. However, their densities are, what to say, for different retinal areas, the densities are different. In the fovea area, there are a lot of cone cells, but almost no road cell. And for other regions, okay, the cone cells decreased quickly, and it was replaced by the road cell. So what does it mean? It means we can sense color only in a small region, and out of the small viewing aspect, we only can sense the brightness. And there are three different types of concept. It is long, so this is the short long cell, medium long cell, and the long concept. They respond to different type of wavelengths. So the short long cell works for sorry. I need to. All right. So because our retina has three different types of concepts, so we can sense three different colors. And for some people, if their concepts doesn't work well, then they will cry. They cannot sense the difference between specific colors. So usually we call it color blindness. So for those circles, there is a number in the circle. If you can see all of those numbers, all of your three types of cone cells work. But if you find there is no number in a certain circle, then your cone cell may cause some colors may not work. Okay, and let's go back to the chart. Okay, let's see. This area is the optical nerve. There is no bone cell, either bone cell or road cell, because all of the signals will through this spot to your brain. Okay. So there's an interesting test. Okay. If you close your right eye and only use close your left eye and use your right eye and look at the glass, okay, with a certain adequate distance, you will see the black circle disappears because the region of the black circle is exactly your neural spot. It is the blind spot. Okay, there's another interesting. Okay, so from these images, but do you see? Okay, do you feel the color this region and the color of this region same or different? Different. Well, great. That's good. But if I remove all of these other color out, okay, I didn't change the colors. They are the same. So now, do you feel the colors are different or the same? set, right? And what's the reason? If you have your laptop, you can try yourself. This image and this image for those regions, they are totally same. I didn't change their value. But your feelings are different. In this image, I personally think this is more like blue, but this is more like green. And this in this image, they are the same pixel values, but our feelings different. Okay, the reasons. Let's go back to the neural system. Because there are a lot of raw cone cell, and they are very dense, and they are very small. So when we watch this image, we cannot use only one or two concepts. We use a lot of concepts, so we cannot control their signals. They need to work all together at the same time. So when we see the region, we will not only see the green, blue stripe, we will also see the pink stripes here. And for this region, we will see the orange stripes here. So when we see the two colors mixed with the green purple color, okay, in our brain, we operate all our retina adjust the feeling of the color. For another example, so checker shade illusion. So there are two blocks, A and B. Do you feel A is or B, which is brighter? Yes, I also feel B is brighter. But again, in fact, they are the same. This is also an illusion caused by our retina and the brain system. We do not only see the black blocks, we also see its surrounding blocks, and our brain processes all information together. Okay, there's another interesting question. So, how we are human? We have 3 different types of bone cells. But how about the rabbit? Rabbit only have 2 bone cells. It's a green and blue. So for a rabbit, it cannot distinguish yellow and red. For them, yellow and red are the same. Then how about a snake? We are human beings. We cannot sense infrared. But for a snake, it can. Their eyes have some receptors which can sense infrared. So for a snake, it is very convenient for the animals to find some other animals in the dark. So this is a mouse. Here, okay. Well, this is simulation image for snake. But this good for them. And how about the birds? Okay. Most birds have 4 home cells. One, so for red, green, and blue, they are similar to human beings, but they can sense ultraviolet. So what is the usage? Okay. For example, the honeybees. Okay. If there is 2 cups of water, it is pure water, and another is sugar solution. For us, we cannot distinguish what's the difference between the 2 cups of water. But for a human hummingbird, it can from at a long distance, it can it can see, oh, there are sugars in the cover waters, and there is no sugar in. Then he can easily found its food. And even for some creations, the Mantis stripes, it can see up to 16 different kinds of colors, and including ultraviolet, infrared, and Polaroid sunlight. So it's amazing. All right, so we now that is a biological. Sorry, and now let's go back to our course because we are computer vision. So we use devices like cameras to get image information. So what is the structure of a color sensor? You see, camera is the mechanical structure, and the component with a digital camera to sense the world is a sensor. And this is different layers of a sensor. At first, there is a micro lens. There is a big lens for a camera, but on the top of a sensor, there are micro lenses. The micro lenses help to gather more light input to the cells on the semiconductor board. The second layer, there is a IR blocking filter. Okay. So why do they need IR blocking filter? The reason is this. As we say, for our humans, our sensitivity for light is around 420 nanometer to 700 nanometer. So that's our limitation. But for a sensor, in particular CMOS image sensor, it can sense a long range of infrared light. So if we want our camera can read the images similar to our human vision, we need to reduce the sensitivity for the infrared. So that's the reason we need a IR blocking filter. Then there is a color filter because for a CMOS image, it only can sense the amount of the input light, but it cannot sense the difference between two different light waves. So we need a filter to allow certain wavelengths, the light of certain wavelengths, onto the semiconductor thing. And finally, there is the converter. It will collect or gather the light and convert it into electronic signal. Then this is the look of a CMOS image sensor. There are many circuits on the chip, and for every cell here, there is a potential wall. This is the region where light will be converted into signals. And then they are analog signals rather than digital signals. So then, different CMOS imaging manufacturers, like they're all analog to digital converting to generate digital signals for further use. So the famous CMOS imaging conductor are Sony and OD Vision and Micron. So if you there are several cameras on your cell phone, and those image sensors are mostly generated made by the three manufacturers. Okay, so this is the other filter on the CMOS research. There are several possible patterns, and the most widely used is the fair pattern. It means for every four cells, two of them are green, and one is red, and another is blue. And the reason for such a design is light of green light is the most actually green light is the most similar to brightness. So they designed the pattern to allow the semiconductor sensor part to have most light input, and therefore to reduce the noise for the another two channels, the red and the blue. So this is the result. You see your most pixels are the green one, and the blue and the reds are the remaining. And there are several different kinds of CMOS image sensor. For the high-end camera, it used the largest one, and the size is 8.6 centimeters square. And for the smaller one, for example, our cell phone, it used the smallest one, and the size is 0.15 centimeters square. So what an advantage of use large CMOS image sensor for large sensors. Okay, it's easy to understand. With a large sensor, you can have a large potential wall, and you can collect more light input to the sensor. Then you can easily get a very clear image with very little noise. However, I want to say for different wavelengths, because our graph is around 720 nanometer, and for the blue line, it's around 400 nanometers. So for different light wavelengths, the refraction index will be different, even for the same length. Then there will be a problem called chromatic aberration. Okay. Although they are from the same point, on the focal length or on the sensing, they will be projected to different locations. And this example, for the horse, take a look of this area. You will see there is a purple fringe. That's because the background of the horse is the sky. There's a lot of light emitted from there. And for the head of the horse is a dark region. So you can see here the purple light will be projected on the sensor, but the red and the green light will not. So you will see the blue boundary here. How to solve the problem? So when you have a cell phone, you also see the ends. There are multiple lenses in the camera set. That is designed for reduce the chromatic aberration. So in this example, this is a type of glass called chrome glass, and another is flint glass. There are two different glasses. And when they are combined together, it can slightly reduce the chromatic aberration. All right, let's take a break. Right. You ready? Can we get started? Okay, so let's make a quick summary. So camera systems are very complicated because they are optical systems, semiconductor systems, and etc. Okay. But for us, because when we focus on the artificial intelligence part, then we assume they are well designed. We neglect or ignore the problems. Let's deal with that. Oh, so for data, if you have an image data, so what's the meaning of those data? Okay, so we need to describe what the data is. So we need to start from color. How do you describe a color? Because color is a feeling of our brain, right? We sense this is red and that is green. But what's the number? How to do it? Okay, so let's go back to the architecture of our eyes. We know there are three different whole cells and rod cell, and they contribute the signals to our brain to know, so sense the color. Okay, so in 1931, it's around almost 90 years ago, there are researchers in France. They try to measure colors. So their approach is very simple. Okay. First, they found some pure light. It means the light has no other wavelengths. The wavelength is fixed. So it is blue, green, and yellow. They specify special wavelengths and project those lights on a small bulb. And they call a lot of volunteers to run these experiments. The volunteer can see the bulb, okay, and there is a the bulb is separated by another bulb. So for the left part, okay, it is combined by the three pure light, and for another one, they use another pure light. So they want to figure out what is the combination of the three pure light will become another pure light. And then this is example an observer can see. So the viewing angle is very narrow, only 2 degrees. And the reason you know is already right. Let's take a look at the when you see too much light, then all of them will processed by our brain and our neural system. So then the experiment will not be accurate. So they restricted the observer can see a very narrow area, and it's almost the size of our fovea region, the region containing the most home cells. Okay, then they create a set called CIE RGB 1931. Okay, so this is their result. They calculate the average of those observers and draw the three curves. It means for a specific light, for a light of a specific wavelength, say this, okay, it can be say 600. It can be generated by combining a certain amount of green light and red light, and the green light wavelength is 560 46, and then the red is 1700. Right, so this is the combination. So now you get the number. For any specific light wavelengths, you can replace it by 3 other wavelengths. However, there is a negative part. So the meaning of the negative part, let's go back to the fact. Because the light is added on one side. And of course, certain light, for this region, the wavelength between 440 nanometer to 550 nanometers. No matter how much red light you add to this side, they cannot make an observer feel the 2 lights are equal. So how to solve the problem? The problem is add the red light to another side in this cycle. So we generate the negative curve. But however, there are negative numbers. It is inconvenient for most cases. So they use a linear transformation from RGB to another set of numbers, X, Y, Z, through this equation. Okay, so they create a color space named CIE-XYZ. Okay, so CIE is the acronym of this organization. So this is French, so I don't know how to pronounce it correctly, but the meaning in English is International Committee of Illumination. Okay. So when we take the CIE-XYZ color space, then all of the numbers become positive. And also we can draw the equivalence functions again. And here, the Y, it has a special meaning. It is very close to luminance. It means the brightness. So take a look of this Y. So Y is equal to a vector, and this is part of the red, and this is part of the vector of green, and this is the vector of blue. So you can see the number is very large, 0.8. So it means what? It means green light in this wavelength contribute the most feeling of brightness to color. So that is also why there is the design for bare pattern, because the bare pattern allows most of the color filters are green. It contributes the most luminance. Okay, so you see there, in concept, we have 2 different things. One is brightness or luminance, and another is color. If we neglect the luminance or the brightness, only focus on what kind of a color is, then this is a proposed solution called big X and small xy color space. So this is the definition. You can convert the X, Y, Z space to the small x and the small y numbers. And you can draw the color gamut. So have you seen the figure before, color gamut? No, not yet. Okay, never mind. So it means, so see the number 460, and this is 620. This is all types of light our eyes can observe. And so this is the pure, what is the most blue color, and then this is the most red color. So once we define the small x and the small y color space for any kind of color, we ignore the brightness, then we can find a position in the color gamut to describe what the color is. Let's see the triangle. It is the three specific light waves, 700, 475, and 546 on the 3 points. So it means for any color, use the three specific light waves, we can interpolate them within the triangle or extrapolate them out of the triangle. So that's the reason why they are negative red color. It means no matter how much of the lights are on one side, we cannot generate the colors for this region. And when you want to purchase a monitor, you usually see there is a spec for 100% sRGB. Okay, so what's the meaning of the spec here? So sRGB is a color space defined by HP and Microsoft in 1996. Okay, and take a look of their region is like this. So for the region is all the colors our viewing lens can observe. And for sRGB, it is this triangle. Okay? It means for a monitor or a display device, the device should be able to generate colors for any kind of colors within this triangle. So for different companies, they define their own color spaces. Adobe RGB is slightly larger than sRGB. It is the green one, this one. And they are also NTSC RGB, the blue one. So NTSC is what? NTSC is the color, is the spec for television set. When we, I should say, around 20 years ago, there are CRT monitor or CRT display. Okay, and there are television companies. They want to deliver their signals to those devices so that users can watch TV programs on those devices. So they need to specify what color should be reproduced on those TV sets. So they create their own color space. Okay? And Apple also create their own color space. Apple RGB is slightly even larger. I don't know the reason. It maybe their products are very good. Okay. So now you have a concept. We have a capture device to capture the radiation of the real world and then convert it into data. And the data is what we are going to focus in the following lectures and classes. And once we have the data, if we want to show the image, we need a display device. From the capture device to the display device, how can we ensure the color captured by the device is the color displayed on the device? So that's we need the color space to communicate between the capture device and the display device. So if both devices following the same color spaces, and we can see this is if the beta E less than 2, it means for this device, the reproduced color will not be far away from the expected color. So this is data means. And however, the whole process is complicated. It consists of several steps. You can find this figure in your textbook. And it's from here. This is the real world. And through our optical system, through the aperture shutter, so this is the camera part. Then the light will be projected on sensors. It can be CCD sensor or signal sensor. Then, because the received light are very limited, but we want some larger signals. Then there's a end. It means enlarge to amplify the signal. Then analog to digital converter. Then we can roll data. However, the raw data may contain a lot of noise. It may not be good enough for us to use. So, and remember, in this year, for every cell, we only have blue, or only have red, or only have blue signal. But we sense one for every point, there should be at least 3 different colors. So there is called the mosaic statement. So generally speaking, it's very similar to interpolations. Even let's take a look here. Okay, we only have some pixels having the green point. So how do you refill the missing points? Interpolation is the easy. And for the red and blue and red, then you can do integration. But the problem is when you do integration, especially at an edge, the simple integration will generate blurry edges. So there are many algorithms dealing with the mosaicing step. And your device, for example, your cell phone, okay, it implements certain mosaic algorithm, but the manufacturers never told you use of them, and then you either did the noise or resharpen the image. And then they are also white balance. It means for different illumination, the cloud or in the indoor or in the clean room, the sunset, white has different meanings. So if we heard about the D50 and the D65, when you go to some shopping center, and there are a lot of light bulbs, and there are at least 2 specific, the D65 and the D50. So D65 means it's not close to this white, and the D50 is yellow. So when we take a picture and our device need to adjust the white, otherwise the image will look like too yellow or too blue. And there's a gamma and gamma. Okay, the step is not was designed for the CRT monitor several years ago, 20 years ago. But we are still using a CRT monitor. Do you know what the CRT monitor is? A big, very heavy, thick monitor. And compare now most of us use the LCD panels, right? And the previous generation of this monitor is very large and heavy. for those devices, the gamma means if you give a certain voltage and you give twice of the voltage, but the brightness generated by the CMOS are twice. They are smaller, so you need to compensate the generated brightness and the input signal. So right now this is, I should say, for most of us, we can temporarily ignore this step. It's not used anyway. And you have a large image data, and if you want to save it in your storage, there is a step for compression, and it depends on the compression format. The JPEG is the most widely used one, and then you save it in your storage. So the sensing pipeline is long, and if you, I should say, in your textbook, there are several chapters describing how to do a JPEG compression. But I think we will not cover those chapters. If you are interested in, since the textbook is free, then you can try to read them by yourself. So let's go back to the basic concept of color RGB color space. So now this is the data part. We have five, and there are a lot of data to describe for some of this image. Okay? And most of you see there are three different channels, RGB. So this is very intuitive step for what R channels means the label of the red light and the level of the green and blue. But keep it in mind, those data in terms of the intensity may not be very accurate, but that's still fine for certain tasks. We don't need very accurate data, color data. Then, so RGB, it is the intensity for every pixel. But for us, we have another explanation for colors. It's for HSV color space. So H means hue, S means saturation, and V means value. So given a color, we explain it like the circle and the brightness. So it's also intuitive from red to green to blue and then come back to red again. And so there are something slightly red and very red. So for this hue and saturation, it's very similar to our gas. So if this is the white point, then this is a very red one, very blue one, and very green one. Okay, and there is another color space called YCBCR. So it is a transformation from the RGB space and the equations of it. Okay, so this is Y from R and G and B from. Okay, the from means it is not from zero. It is from a specific number. The Y starts from 16 to 235. But why do they define those numbers in range? Because the color space was defined is very useful for TV and the JPEG format. So why do they define the range? Because they want to highly compress the data. They don't need the full range. And then in particular for TV, when the TV set or TV channel are just established, it's very expensive to deliver those signals from TV station to users' home. So they want to reduce data as much as possible. And what is the advantage of this space? It means when you convert an RGB format into YCB-CR, so Y is the brightness, and the CB and the CR, then channel of blue and the channel of red. Okay. In this example, you can see most of them are highly similar to their nearby pixels. So they can subsampling this to reduce the image to a smaller size. And so that it can reduce the data required to transfer. And this is another color space for the CI star A star B star. Okay. So the color space, the advantage is it is perceptually moved. It converts the RGB space to color A and T. Okay. So for the brightness part, you cannot sense any color. And for the darkest part, again, because for most of the when you enter a dark room, you cannot sense the different colors. You only see that they are all darks. However, the conversion from RGB to this space is non-linear. In the equation is here. Okay, so you can see this is a non-linear function. And here we don't need to. I do not expect you to remember those equations. Because the screen is cropped from your textbook. If you want, just open your book and you can easily find this equation. What I want to show you is, okay, you can create any kind of color space, and then for different purposes, there are different color spaces for you to use. And for this X, CIE and AB color space, let's go back to their gamma again. So you can see there are many ellipses from. The meaning of the events in the color space for this LA star B star. If you make a shift from a point to another point in the LA star B star color space, it's very similar to from a point to a nearby point. So once we have the LA star B star color space, so that's the reason we say LA star B star is a uniform space for any 2 points within the space with the same distance. They will be the same in the color gamut. As for if we use color gamut, you will see the shapes of those ellipses differently. But in the X, L star, A star, B star color space, they are the same. So it's easier for us to measure the difference in perception for 2 colors. So, okay, then for us, when we use the data, what is the most where is the most important channel of the information? Okay. So there are 2 choices: intensity or colors. Let's take an example for this image. If I show the color only, it means I set all of the brightness or intensity the set. That's what you will see. And if I replace the color or the set, but preserve the brightness, then this is the result that you will see. So this you can see most information of an image is contained in the brightness channel. In particular, on the edge. So, for example, on the road, most of the intensity are the same. On the skies, all of them are the same. Under the shadow, there are no difference. So, where is the information? The pieces of information are on the edge. So when we take a look at an image, we find information on the change of intensity. Okay, and how do we represent it? So it's example. Yeah. So this is the unit of the image. It's called pixel. We use the number for for a lot of points on the image. So this one is this pixel is here. So you can see in the center, the number is smaller, and around the corner, the number is larger. And now we are okay. So now we have a number for an image, in particular intensity image. So now we are going to find a few methods to deal with the image in terms of those numbers. So in filtering, this is a very basic approach to deal with visual data. And it can be used to, say, denoising and find some signals from the images, or just enhance the image. And there are many different kinds of image filters. And the most simple is the simple one is the linear filter. This means we just use the surrounding areas to combine those values to replace the intensity of the pixel at the center. In this example, so this is Google Meet. I think most of them are familiar with this program. And this is a function because you can blur the background. So it's a useful part because for some cases you don't want your participant to pay too much attention on the background. You want your colleagues or friends see you rather than the background. And another example is this is for motion. To see the background, you have a feeling, okay, the cyclist is moving forward quickly. And this is a movie ad flash, okay. And you see the long line at the background. It also gives you a feeling, okay, the guy is moving very fast. So how to do it? Yes, okay, there is a very simple filter called fast filter. You can just for a central pixel, use the surrounding edge pixel in itself to calculate the sum and replace it. And this is an example that makes you feel. So for we want to calculate this pixel, then is the area of this region, and the result is 0. And okay, another 10. another 20, 30, 30, and this. So what should the number is? 50. 50. Let's take a look. Right, very good. And this? Good, good. Okay. And then when we take all of them, then this is our result. Box filter. Okay, so what they do is it just replace the central pixel with some values taken from the surrounding pixel. And what can it do? It can remove the gap features, and this is an example. So the left part is the input image. Okay, and you can see there are a lot of pages of. But the right part is the result of box filter. The high frequency signal, all the edges are reduced. So let's take a look of the similar. Let's see some properties of linear filters. Okay, so this is the original input. If I use the filter kernel, so what will be the result? Any suggestion? Okay, let me explain. So given an input image, if I use a filter with its coefficients as 0, 0, 0, 0, 1, 0, and 0, 0, 0, then what will be my generated of filter? Okay, fine. So the answer is nothing changed. Because you see, if you for every pixel here, you times the 0, times the 0, 0, 0, then those pixels contribute no values to the central pixel. And for the central pixel, it ties itself. So the result is the same. And if I have another filter, okay, most of them are 0, only at the right pixel, the value is 1. Then guess what we get?
The picture is shifted.
Good, very good. The picture is shifted. And okay, let's take another. If we okay, so this if we use a filter, but the filter is the values 2 at the center and the minus all surround all values in this region. Say imagine what we will do. So the value in fact here is negative 1 nice, negative 1 nice, negative 1 nice, negative 1 nice, and the 1 and 9 a nice and negative 1 nice for best equation. What we will get. Any idea? Great, great. So more sharpened image for next. When the central pixel is bright, it becomes brighter. When the center result is dark, it becomes dark. So we generate the enhanced or sharpened result. Then let's take a look. So this is original image input, and this is sharpened image. And how about this filter? One, two, one, zero, 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 -1, -2, and -1. Okay, so you can think it this way. So if this is a smooth region, for example, like this one, and the background is very smooth, or the pure white region. So there is each filter. So what is the expected result? Then all of them are 255. Then 255 times 1 plus 0 plus -255. And 504 plus 0 plus -504 and positive -255 plus 0 plus -255. So it will be 0. That's okay. And then, so for smooth region, the result is 0. And how about for edge? For the vertical edge. Vertical edge means the left part is large values, and the right part is small values. So large value times those coefficients, and with small values times those negative coefficients. So what will be the result? And hence idea.
Maybe the edge will be sharper.
That's right. That's the edge will be sharp. So that's the look. Okay. So for smooth regions, you will get 0. And for edges in in particular the vertical edges, we will get either large positive values or large negative values. So here is the absolute value. So either large negative or large negatives, we will see the brightness here. So with this filter, what you can detect? We can detect the vertical edges. And how about this one?
Horizontal edges.
Very good. So the result is horizontal edges. And so use image filter, we can detect edges. And this is a simple filter for vertical and horizontal directions. And there's a family of image filter for stereo filters, because vertical and horizontal are just the two directions. If you can design a group of filters for any kind of directions, then you can detect any kind of edges. Okay, then let's see the best gradient filter. So you just see two examples, right? And the number there is 1, 2, 1, -1, -2, and -1. It has a name. It's called solvent, because it's developed by the researcher solvers. And in general, if we have the negative and positive value on the two sides, then it can be used to find edges. But because for edges, it means a significant change in intensity. And okay, so let's see some example. So the three filters are also filters, but they are not nonlinear. For the first one, you can sum the four adjacent neighbors plus one. So the ij are the index of the image. And the G of ij means the value, the new value of the pixel. And the F is the original image intensity. Okay. So, okay. All right, so there is a question. Let me ask you first. Why is this filter nonlinear? You don't need to answer it right now, but keep it in mind. Why is this filter nonlinear? This group looks like a linear, but it is not. It's fine. It's fine. Just keep it in mind. And for the second filter, you can sum the square value of the 3x3 windows. Okay, this means for K and K means the shift and the 3x3 window. So that it can be -1, 0, and or +1. Plus it to the original coordinate I and Z, and then calculate the square and sum them up. This is also a filter, but it is not linear because this is a square term, right? So of course it is not linear. Or you can calculate the difference between two adjacent pixels. If it matches sign criteria, then you set the result as 1. Otherwise, you set the result as 0. This is also a filter, but it is not linear. So, and you will learn, or have you learned convolutional neural network? You have learned it, right? Okay, so this is a method. Let me take a survey. You heard about it. Convolutional network, PV. Okay, you heard about it. Okay. And you know the definition of convolution. Give me 10. Okay, so most of them are not confused what convolution means. Okay, so convolution means you have a bunch of data set, and then you have a convolution kernel, and you will use the convolution kernel to create a new set of data. So, but it can be done in 1 dimension, 2 dimension, 3 dimension, 4 dimension, 6 dimension, etc. And the mathematical definition for 2-dimensional convolution network is this. So F is the image, and the K is the kernel, or the window size. You just take a look. And then the convolution will use the negative minus operation here. So it will generate a new image. And for filter or correlation operator, okay, this is plus. All right, let's take a break. All right, so let's get started. So these are the definitions of the two operators, correlation and convolution. So do you feel they are very similar? Almost the same, except for the operator of correlation, the operator here is plus, but for convolution, this is the minus. Okay. And let's take the back of our filter. When you calculate the age, do you use correlation or convolution? Say again. Some people say, someone say convolution, and other ideas. Okay, let's take a equation. Okay, so this is the image, and this is the kernel. This is image, and this is the kernel. Keep in mind this is the plus and the minus. I check back to the when you calculate this. When you have an age here, and then this is the bright part, so say a very large number, say 255, and this is smaller. And then what do you do? You times, you use 255 times 1 or -1. You times 1, right? So in this, you use a part. When you say the k, so in this case, k is -1 for the horizontal axis. Then you use positive k or negative k. So if this is negative, k is mean -1, you find that the left pixel. But in convolution, if k is -1, you use the right pixel. So in this case, you use the left pixel or the right pixel to calculate the filtered value. The left or right. So in this case, you are using the correlation operator. So they are mathematically equivalent, but they have different definition, just definition. And they have different symbols. So this is a symbol for correlation, and this is a symbol for convolution. However, they can exchange by this way. Okay. So there are some properties for linear filters. First is linearity. So this is why we call it a linear filter, because if you have two kernels or two filters, you can combine them, and that means if you have two images, F1 and F2, and you have the filter H, then you can combine the two images at first, then apply the filter. The result will be the same as you filter for the first image, and then the second image, then combine the definition. Okay, so let's go back to this one. I say this filter is not linear. And why? Why does this filter not match the definition of linearity? Okay, let me explain that. Okay, keep it easy. If you sum two images up and apply a filter, the result will be the summation of two images on the set filter, right? And take a look at this. Okay, that's right. Good, very good. So let's see something. If I give you a black image, all of the pixels their values are 0. Then when you use the filter and here, so when you sum up two dark images and apply the filter, you will get a new image. All of the pixel values 1. But apply the filter to the first image, you will get an image with value 1. And another is also value 1. When you sum it up, the value is 2. So that filter is not linear. And the linear filter also has another property called shift invariance. It means if you have an image F and you generate another image G just by shift the pixels, and when you apply the filter on the new image, it will equals to when you shift the image and apply the filter. So linear filter has the property, is to say it's very because of the linearity, this is very easy to say use. And more because of the linearity, then there are some other properties communicated. It means you can just switch image as a filter and the filter as an image. Okay? And then they are associated. That means if you have an image and have 2 filters, then you can just convolute the 2 filters and then apply to the image. It will be the same result as you apply 1 filter at first, then apply the second filter. And then, so you can combine. So if you have 3 filters, you can combine the 3 filters at first, then apply to the image. And then there is a addition property. This means if you have 2 filters, you can sum them up, and the result will be. So this is very similar to the linearity. And if you have a scaling factor alpha, and you can adjust your input image, or you can apply the scaling factor to your filter, and the results will be the same. And this is an identical property. It's just the same as the question asks you. If you apply this filter to your original image, you will get identical image. Okay, and we see all linear filters. One is very important and widely used. It means Gaussian filter. Do you know Gaussian distribution or normal distribution? They are the same. And for 2D, so this is the distribution of normal Gaussian in the 2D space. And the sigma here is the radius of the kernel. So if I say this is a 5 times 5 filter and the sigma value is 1, then this is the generated result. If I use different gamma value, then if I set a small gamma value, then the distribution of the Gaussian kernel will be sharp, high, sharp. And if I use a large gamma value, then large sigma value, then we'll because sigma means the standard deviation, also the width of the kernel. So if I use a large sigma value, then my distribution will be flatter but wider. When we apply different Gaussian filters to an image, then for the input image, for sigma is 1, so this is the result 2, 5, 10, and 30 pixels. So you can see the difference. With a larger Gaussian kernel, then the filter will become larger and flatter. Your generated result will become more blurry. So let's recall this figure. So when we discuss about the length, okay, we say length as a property. If the aperture means the depth, the distance between the two blocks. When we have a large aperture, our background is become blurry. If we have a small aperture, the background will become clear. And the reason is why. Okay, let me explain the reason. It means if the object is not on the focal length, so this object is the flower here, and this is the background, then the light emitted from the background object through the lens will not focus on the film or the sensor. So there will be a range of the light. And for a large aperture, the range will become larger. And for a small aperture, the range will become smaller. Say if there is a triangle, then for a large aperture, the triangle will become larger but blurred. So it's the same as we apply a large Gaussian filter thing. So let's go back to this image. If you want to say we have an application for it, this is the application for applying Gaussian filter to the background. So we need to decide how large the kernel should be, right? And now we have a knowledge of if we use a larger kernel, then the background will become blurry. And let's go back to the Google Meet application. You can see this is the button, and then there is another button. So this means if you click this button, you will get blurry background. If you click this button, you will get a relatively clear background. And so how do they control it? They can just adjust the kernel size. And okay, you know, Gaussian distribution, it has value of a very long distance. It means the infinite support. Okay? But in practice, we need to decide filter window size. So what should be the window size for Gaussian distribution of Gaussian kernel? So usually we will use the rule of thumb. It will set the kernel size will be 3 times. Sorry, window size will be 3 times of the kernel width. And let's make a comparison between Gaussian filter and the box filter. So this is the result of Gaussian filter. And this is the result of box filter. Can you see a different? So I think the objective result is not very clear for the difference. So if you have a laptop, or maybe it will be clear on your laptop. So what I want to show you is if you apply a Gaussian filter, you will see no blocking edges in your output image. But if you apply a box filter, because there are edges in the filter, so the generated result, you can see there is some grease on the. So what does Gaussian filters do? So it removes the high frequency component from the image. So it has another name because low pass filter. And let's take a look of this image. So this is the filter we use. Okay, it will enhance the central pixel. So you will get a sharpened image. The filter has another name called the high pass filter. It will let the high frequency signal enhanced in the generative result. And the Gaussian filter do it on the opposite way. It removes the high frequency. So this is a low pass filter. And there is another practice. The convolution of a Gaussian filter is still a Gaussian filter. So it's very similar to this property we see before. Yeah. So if we have a Gaussian filter, another Gaussian filter, and the third Gaussian filter, when we convolute them together, they are still a Gaussian filter. The change is just the sigma value for the kernel width. So, and the Gaussian filter is a separate filter. It can be separable to 1D filter. And okay, so this looks like this is the mathematical definition for Gaussian filter. And it can be the product of two Gaussian filters. And for this one, there is no y. And for this one, there is no x. So this is the Gaussian filter for because x is the horizontal vertical axis. So this is for one dimension. The y is the vertical axis. So this is for another dimension. So this is all a separability of a Gaussian filter. And we will keep it in mind. Gaussian filter is a separable filter. And the separable filter has a very good advantage. Then let's show it. Okay, if you want to apply a Gaussian filter on the image, say a very simple image like this, then you need to calculate those numbers. And then if we separate a Gaussian filter into two 1D Gaussian filters like this. This is the vertical line and this is the horizontal line. Then we perform filtering along rows and get this result. 1 to 1 times the image, and we will get the value. And if we apply the vertical filter again to the result, 1 times 11, 2 times 18, 1 times 19, sum them up, the result is still 65. The same is the one if you compute in the pixel value individual. So why? So what is the advantage of a separable filter? So let's take a look. Okay. So if we have a kernel filter, its size is k by k pixel, and then we have an image, its size is h times w. Then if we need to calculate the pixel values individually, then we need k square multiplication times k square addition. The k here is 3 by 3. So we need a time multiplication for 1, 2, 2, 3, 1, 3, 2, 3, 4, 5, 2, 5, and sum them up. But if we separate the 2D filter to two 1D filters, then we only need K times for first, we calculate an intermediate image like this one. This is the intermediate image. Okay. Then we only need K multiplication plus K addition for the intermediate image. And then we calculate another one-dimensional field for the intermediate image. Then we will only need K multiplication, K addition. So in total, we only need 2K multiplication and 2K addition for the entire spectrum height and width for the generated image. Compared with the computational load here, it is much smaller. So that is the advantage of a separable image field. Okay, in practice, when we apply a filter, say this, and their boundary, this is the kernel. So what should we do? Is we are going to calculate the pixels on the boundary, because you see there, if you want to calculate this pixel, and the filter is 2 here, but there are no pixel available out of the image. So what should we do? There are 4 different solutions. The first means keep it blank, like this one. Okay, we extend the boundary, but there will be no value. All of them are 0. And if we apply a Gaussian filter here, then we will generate the black or dark boundaries. And the second one is wrap around. It means okay. It means for a pixel here, we just sorry, this is image. No, this is wrap around. It means from a pixel here, we use the pixels from the beginning to fill in the boundary. So this is a rapid extended image, and if we apply the Gaussian filter on it, then this is generated, and we cut the edge out. So this is a final one. And the third method for named copy image edge. So for the extended boundaries, we copy the values in the inside the original image, and it just extended it. Then apply the Gaussian filter and crop the boundary out. So this is general result. And the latest one is called reflect across edge. So this means for the inside pixel, we flip it out. Then apply the filter, get the output images. So for handling the boundary cases, there are 4 different types of pixel extension. Okay, so that is linear filter. So for non-linear filter, there are one of them is very famous for median filter. So what it means, if we within the filter, we find the median base. Okay, for example, for this patch, there are 9 values and we saw it out. So the smallest is 1 is 10 and the largest one is 90. We find, okay, the median one is 27. Then we replace the value of 97 with 90 with 27. So it's median filter. And the advantage of the median filter is, okay, it is very useful for removing the outliers. So for example, this is if we just take the 1D data as a reference, this is the outlier, and we want to remove it. So if we apply median filter, then okay, it will be replaced by some other pixels nearby. If we apply mean filter is very similar to Gaussian filter because it's a linear. Then all of the nearby values will be enlarged. So this filter is useful for specific noise like this one. If we have an image, okay, it's clear. And if there are noise, particular the dot and the pattern noise, it means the noise is either very large, the bright one like salt, or the very dark one like pepper. Then if I apply Gaussian median filter on it, then I can remove most of those noise. And I want to show you a live demo. Okay, so this is Medley. And are you familiar with this software? Okay, and this it's not free. It's very expensive, but you can use it because our university purchased the license. You can download it from the CGU software website. So once you download, this is my example code. So I will read the image pattern here, and then I will convert it from RGB to grayscale. Then I add noise, the pattern and sort noise on the image. Then I apply the median filter to remove this image. And I want the generated images. This is the filter image. This is the noise image. And this is the input image. You see the differences. Okay. And let's compare the input image and the filter image. So this is the input image, and I set the title of the figure as image gray, and this is image filter. So most of them are similar, or visual perception, but pay attention to some regions like this, or like this. The filtered images are slightly blurred because median filter replace the pixel value with the median value of the surrounding. So let's see. Unfortunately, this one. Okay. There is a black spot on the paper, and it is not noise. It is just a dark variable dark hole. And the median filter removes the black spot. let me say, MATLAB is an expensive software, and OpenCV is free. So do you see the difference? And I should say, if you have experience in Open, use the MATLAB, raise your. Okay, put one. Okay, so because most of you never use MATLAB before, so let me briefly introduce it. So MATLAB is a commercial software developed by a company called MathWorks. Very expensive, and because compared with OpenCV, OpenCV is developed by a community. It is first supported by Intel and all other. OpenCV use Python, and Python use a lot of packages. One of the problems of Python is there are a lot of different versions, including the associated packages. And for MATLAB, the advantages, it is maintained by a single company. So all of the scripts are very short, precise. It's very easy to generate the figures or chart. Say, for example, this one. Okay, for the two figures, they are generated by MATLAB. So MATLAB is a tool very easy for users to generate the figures or graphs, and they are very elegant. So there are many books they about image processing, and they use MATLAB as the program for image processing steps. And because you can access it on your campus because you are a student, you have an account. Or university purchase it already. So if you want, you can download it and install it on your own computers to run it. All right, so let's see the difference between median filter and the Gaussian filter. So given an image and with some noise, if we apply Gaussian with a kernel size 3 by 3, so you can still see the noise and the background region because the background is dark. So Gaussian filter, it is the weighted average surrounding pixels. So we cannot totally remove those noise. But with the median filter, if we set a small filter size 3 by 3, we remove most paper and soft noise. But with a larger kernel size, we also remove some details. For example, I think this is a rock or something else. The surface of the rock become very unclear. So there would be a question: what should we set the kernel size of the median filter? We don't. Okay, let me recall what we see at the first class. Yeah, this is the question is similar to the experiment here. For this algorithm, what is the best parameter for the kernel? I don't know. I need to try. And for the TDR algorithm, the same. I don't know. I need to try. So for a median filter, it's the same. I don't know what is the best kernel size, and I need to try. All right. Okay, then this is a bilateral filter. It is highly related to Gaussian filter, but it's slightly different. So let's talk about the definition. So you see, this is the Gaussian filter, right? So if we apply Gaussian filter to a smooth region, then it will generate a smooth. This Gaussian filter is a weighted average for surrounding pixels. If we apply the Gaussian filter to an edge, then what's the result? The edge is also blurred out. If we apply Gaussian filter to a texture region, it is also blurred out. So how to improve, how to revise the Gaussian filter? Okay, their idea. So this is a paper published in CGU. Their idea is they developed a bilateral filter. Then for a smooth area, they apply the whole Gaussian filter on it. The generated result is smooth. And for an edge, they apply a Gaussian filter, but only for part of it. So see this filter. For the right part, all of the associated the factor are zero. It removes the scaling factor. And for the left part, it is still a Gaussian filter. And for textual region, some factors are high, and some of them are almost zero. So then the result will be, okay, they preserve, so this is an edge in the input image. And then this was the edge of the output image compared with the original Gaussian filter. The edge disappears. But if they apply the lateral Gaussian filter, the edge is preserved. So that is the finding. If they can develop the filters pixel by pixel, then they have the opportunity to preserve edges. So the next question would be how to create filters pixel by pixel. And for this, they apply a filter for all pixels, right? And for lateral filter, they apply different filters for every pixel. And then they propose method is or they use two different Gaussian filters. One is the original one for space. Okay, and this the Gaussian filter you take a look at for the previous slides. But for another Gaussian filter, the IP and IQ means the intensity of the pixel and its surrounding pixel. So let's take a look at here. Okay, this is the input image, and this is a patch. There is a central value. Okay, there is a central pixel, and the pixel at the center is very high, around 255. And then they can calculate every pixels in the image filter to see the difference of the intensity. So this is a term. If the pixel at the center is very different from another pixel nearby, then the intensity difference will be very large. When the intensity difference is very large, then the Gaussian distribution will be very small. Take a look at this. Okay. when the value is large, the Gaussian distribution, the value will become very small. When the distance is very short, the weight is very large. So here is if the difference is very small, then the weight is very large. So like this. The difference of the intensity at the right, the left region, because all of them are very bright. So the intensity difference are small. So their weight is large. And for the right part, because they are all dark pixels, the intensity difference for a pixel here against its central value is very large. So the weight becomes very small. So the weight is controlled by the second term. And then so this is the range weight, and this is the space weight. So for this example, okay, so if we take a 1D example, so 1D means in the 1D space, if this is the intensity, so there is an edge, the intensity changes a lot. And there is another edge, the intensity changes. So this is dark pixel, so the value is dark here. And this is bright, so the intensity becomes large. And it gradually becomes dark, and then the intensity gradually goes down. And this is all bright, so all of the intensity is high. Then when we apply a Gaussian filter here, okay, this is the Gaussian filter for space, and this is a Gaussian filter for intensity. So for the part, because the P point is intensity is high, and the Q point and the intensity is low, the difference is large. Then the weight here becomes very small. So apply this we show it in 3D space in the lab. So this is the Gaussian filter for space, and this is the Gaussian filter for intensity. We combine the Gaussian filter, it will generate this result. And this result is this. Like this one. When you apply the filter on the edge, you will generate a shape. For the half of it, almost the same. For another half of the part, this looks like Gaussian filter. Like this. And then you need to control the parameters here. This is for the space, and this is for range. Again, how to tune the parameters? Nobody knows. You need to try the value for the first one, for the value for the second one, and find the optimized parameters for the image you want to use. And then, because for space and for range, there are two different Gaussian filter, Gaussian distributions. So when we apply the bilateral filter here, it will not be a weighted average for all pixels nearby, because for this part, it will not contribute the original value to the new pixel. So it will preserve the edge. And this is the example. So given an input image, we will try 3 different range parameters, 0.1, 0.12, 5, and very large, where infinity. Then you will get the 3 different ranges. And then you try the space kernel size 2, 6, and 18. You will generate the different image. If you set the 2 very large, it is almost the same as the original Gaussian filter. But if you select the proper parameters, you can generate the images like this. You preserve most edges and smooth the texture or flat area. Okay, what can the filter be used? Let me show you an example. Okay, this means flash photography. It means you have a camera, and then in a dark room, you take a picture. If you turn on the flashlight, then you will get a bright image. But because the flash is too bright, so the color is not accurate. Like this one, the left part. This is the result of a camera taken on a pen with flash. And then the left part is you use the same camera, take picture of the same object, but turn off the flash. Then you will have a lot of noise because in a dark room, you need to increase the gain. Remember, there is a gain or the amplified factor for the CMOS image sensor. So this is noisy, but the color is good. The color is not accurate in this image, but the edge looks good. Also, we want to combine the two images together to generate a new image. So this is photography. It is a part of the computational photography. So how do they do? So this is their algorithm. This is a non-flash image, and this is the flash image. They apply bilateral filter here to generate an image full of detail, like this one. They preserve the edge. And for the non-flash image, they also apply bilateral filter here. Again, they will generate the base image. So this is the base image. Okay. Then they fuse the two images to generate the output image. So in the output image, you can see for the smooth area, the color is good, but there is no very obvious noise. And for the edge is clear because it is used data from the flash image. So this is one of the applications of bilateral filter.